spontaneity of chemical reactions. That's what we're talking about. Most spontaneous processes, not all, are exothermic, that is, heat is released. Endothermic reactions, where heat is absorbed, tend to not be as favorable for spontaneity. Reactions tend to occur in a direction to decrease the energy of a system. That makes exothermic reactions favorable. Just think of a ball rolling down a hill. The ball starts at a higher potential energy up here, and in a gravitational field, there is only one way that ball is going. It's going downhill to release energy, and we're equating that with an exothermic process, and we're saying that is the most favorable. All right, but that is not the only factor. So here are reaction progress diagrams. They're also known as reaction coordinate diagrams. And what they're depicting here is a reaction. It could be any kind of a reaction. Over here on the left side, we have our reactants. So these are our reactants. There's an energy barrier to all chemical reactions, which we call the activation energy. You're going to learn about this when we study chemical kinetics in the next chapter. But needless to say, let's say I did want to roll a ball down this hill. The first thing I'm going to have to do is push it up the hill to get to the top. We call that the activation energy. And just to let you know, the higher that hill is, the greater the activation energy, which we actually designate as E of A, the slower that reaction will be. But in the end, if the original reactant energy is higher than the product energy, that reaction is exothermic and has a negative delta H. That is an exothermic reaction, and that tends to be favorable. And this is just reaction progress. And we can actually, you're going to learn about this, we can actually measure the delta H as the difference between the product energy and the reactant energy. We do that, we measure that delta H by taking the product enthalpy minus the reactant enthalpy. And you can see that the reactant enthalpy is higher or a larger value than the product energy. So when we measure that delta H, we're going to come out with a negative delta H, and that's indicative of an exothermic reaction because our reactants have given up heat. Energy has been given up or released. And then we can go over here and we can look at an unfavorable reaction. This is an endothermic process. You can tell that because our reactant energy is lower than our product energy is. And we have a very big activation energy here, E of A. Here's our product energy. This is going to be a reaction that absorbs. So energy in this reaction is absorbed. So you have to add energy just to get it to happen. And in the end, overall, energy has to go into the system. It's not released, it's absorbed. And this is typically unfavorable for what we call spontaneity. So when we're calculating delta H, we've got a product enthalpy which is larger than our reactant enthalpy. This would be our delta H for this reaction. So the product enthalpy is a larger value in this case, and we're subtracting a smaller value in this case. So that's going to be a positive value, and that is endothermic. Okay, delta H is positive. All right, let's talk about this strange word which you've undoubtedly heard before entropy, and we're going to talk about entropy with respect to solution formation. We will talk a lot more about entropy in much more detail in thermodynamics later on in the course, but let's talk about it with respect to solution formation. So first of all, just consider a couple of things. There is this natural tendency for matter to spontaneously spread out, for things to become mixed up. It's very improbable that you will have a pure substance. Nature loves mixtures. That's what it does. It stirs things up. A frequent comparison is cleaning your house or cleaning your room. It has a tendency to just get messed up unless you put some energy into the situation. So matter has the tendency to mix, to spread out. Solutions have a natural tendency to form spontaneously because what you're doing is you're increasing the entropy, or what we can refer to as disorder. It's just more probable for things to be disorder. And you can think of it in terms of hot objects spontaneously release their heat to the cold, to the surroundings. For instance, if you open up your front door in the middle of winter, it's not that the cold is coming in. It's that the heat in your 70-degree house is going out into the 20-degree cold. It doesn't happen very often in Texas, but it does happen on occasion. Gases will spontaneously expand. So if I open up a bottle of perfume, that perfume will expand, and eventually people will smell a few molecules of the perfume and be able to detect it. Odors do that. Okay? All kinds of odors. All right, entropy is a measure of the spread, the randomness of matter and energy. And it can be matter and both energy when we're talking about entropy and the natural increase in disorder. So reactions always tend to spontaneously maximize the entropy of the universe. If something is occurring, for instance, you are alive right now. Now you are an amazing mixture and combination of things in a very ordered configuration. But in the process of being alive, you radiate heat. And that heat is expanding into the universe, never really to be recovered in the useful way. It just becomes more and more disordered as it expands. And how do you do that? Well, you eat and you metabolize your food and you convert that into a lot of order, but at the expense of all the waste heat that you allow that your body spontaneously allows out into the universe. So that is the second law of thermodynamics. It's a really, really big deal, and it took quite a while for scientists to work out how the universe actually worked. And when we get to thermodynamics, we'll talk about some of them. All right, entropy and solution formation. So the final step in solution formation involves mixing. And mixing, guys, when we mix that solute and solvent, we have lower entropy, and that's over here and over here. That just means order, fewer possible arrangements. So in both cases, we have fewer arrangements that are possible. But when things mix, when a solution forms, because you have different kinds of particles that are distributed throughout the solution, you have more possible arrangements. And more possible arrangements are more likely. And the more likely a situation is, the higher the entropy. And that's really what we're talking about. This is more probable. This is more probable than pure. Okay? As soon as you mix these two together, the more possible arrangements occur from the mixing. Okay? This inherently increases the entropy, and we'll just use the word disorder for now, or more possible arrangements of the system. Okay? That's what mixing does for you. It increases the disorder, the possible arrangements, and that's just more probable than something being pure, given the opportunity to be more disordered. So process of dissolution involves 4 separate energetic processes. We've got to break the solvent-solvent interactions. We've got to break the solute-solute interactions. That's unfavorable. And then we have the new solute-solvent interactions. The components are mixed together, so they do have some form of bonding that goes, and that releases energy. So this is always going to be endothermic, and this is always going to be exothermic. But overall, if I add that up, add these two endos and exos up for any particular solution formation, would you expect overall solution formation to be exothermic or endothermic, given that exothermic is more favorable?